A very good day to all. I happily welcome you all to the 19th and valedictory webinar of Raman Optronic Webinar Series, ROSE 2023, organized by Raman International Optronic Society, RIOS. Today, we have Professor Sajeev John from the University of Toronto, Canada, as our distinguished speaker. Now, I welcome the RIOS chairman, Professor Shankaraman, for the welcome address.
Thank you, Dr. Sukna. Most respected Professor Sajeev John, Department of Physics, University of Toronto, Canada. Respected professors, members of Raman International Optronic Society, RIOS, friends, organizing committee members, students, and esteemed participants of the webinar. RIOS was formed with a vision of global interaction and sharing of knowledge in photonics, optoelectronics, and optical communication, with a mission to provide a platform to bridge the gap between academia and industry through collaborative research, webinars, and research paper presentations. Now, there are more than 1,500 members in RIOS. With this vision, RIOS started organizing Raman Optronics Webinar Series, ROSE, a virtual international conference since 2020. Every year, we start ROSE on the birthday of the legend Sir C.V. Raman, November 7th, and the series lasts for about 1 month. Today is the last day of the 4th ROSE. Nowadays, organizing webinars and conferences have become a means of making money. In a way, I call it webinar pollution. Every day, we get a lot of invitation for such webinars and conferences asking $500 to $1,000 as registration fee or participation. How can poor students without any financial support attend such international conferences? It is in this context, ROSE stands unique in several aspects. There is no registration fee, no membership fee. Also, there is no repetition of speakers in ROSE since 2020. Every year, we come up with new eminent faces in optoelectronics. Based on the feedback received, all the webinars in ROSE 2023 are scheduled at 7 p.m. IST on all working days with the same Google Meet link. Beyond every success story, we see the perspiration of a dedicated group. Today, I am extremely happy to see the successful completion of ROSE 2023. Thanks to all the RIOS members. I am greatly indebted to Dr. Amar Swapna and Dr. Rajiv K. Dhaman, who are with me since 2020 in organizing ROSE and forming RIOS. Now, Dr. Swapna is in the University of Nova Gorica, Slovenia. Actually, she is managing everything on my behalf, right from inviting resource person to the smooth conduct of the webinar. She had spent more than 5 months for organizing ROSE. Dr. Rajiv K. Dhaman has proven his potential in the systematic organizing of ROSE by heading the technical section. In this occasion, I would like to thank Dr. Amar Swapna and Dr. Rajiv K. Dhaman. I am also thankful to the organizing committee members at University of Kerala, Mrs. Ashwati, Sri Lakshmi, Sister Anju Abraham, Anasura, Donna, Ritik, who took much pain in sending reminders, collecting feedbacks, issuing certificates, and preparing the abstract without any complaint. I am also thankful to Mr. Ajit and Gokul, who were the people behind the YouTube live of the webinar, recording, editing, and uploading the videos. It is only the hard work of the team behind the success of the webinar. RIOS greatly acknowledges their contribution. I take this opportunity to thank Professor Unnikrishnan Nair, the founder Department of Optoelectronics, University of Kerala, for his advice and active participation in all the ROSE webinars since 2020. I thankfully acknowledge the support extended by Professor Karanjit Singh, Punjabi University, Dr. Humberto Cabrera, ICTP, Italy, Professor Dharimveer Chaudhary Devilal University, Haryana, Dr. Svetlana, Russian Academy of Sciences, Professor Radhakrishna Prabhu, King Gordon University, Professor Josrajan, University of Malaysia, Professor Babatunde Emmanuel, Lead City University, Nigeria, Dr. Sunny Matthew, Marian College, Kutikanam, Dr. Bina, Newman College, Todubida, Dr. Sesidaran Alasar College, Todubida, in the successful completion of ROSE 2023. On behalf of RIOS, I once again thank all the organizing committee members. The results of the research paper presentations conducted on 25th and 26th November 2023 will be announced now. The abstract book, the ISBN of ROSE 2023 can be downloaded from the website, and the results of the Best Paper Awards can also be viewed in the notification page of the RIOS website. A humble request to all the RIOS members, all of you can suggest eminent scholars in optoelectronics as speakers in ROSE 2024. We welcome your valuable suggestions and nominations to enrich RIOS and ROSE. We are also happy to associate with the academic activities upholding the vision and mission of RIOS. Let us join hands to strengthen the optoelectronics fraternity. Coming today's webinar, today we are fortunate to have the giant in optoelectronics, who is regarded as the father of photonic bandgap structures, is Professor Sajeev John, University of Toronto, Canada. He is with us as the speaker. I am proud to say that he originally hails from Tiruvalla, Kerala, India. He is the co-inventor of the concept of photon bandgap materials in 1987, providing an easier route to his original conception of the localization of light in 1984. We are thankful to you, sir, for accepting our invitation to the webinar. On behalf of RIOS, I welcome Professor Sajeev John to the webinar series. I also extend a warm welcome to the esteemed professors, researchers, students, and all those who joined the valedictory webinar of ROSE 2023. Now it is time to declare the Best Paper Awards for the research paper presentations in the 7 technical sessions held on 25th and 26th November 2023. I invite one of the secretaries of RIOS, Dr. Emma Sofna, Laboratory of Environmental and Life Sciences, University of Nova Gorica, Slovenia, to chair the session and to announce the result. Over to Dr. Emma Sofna.
It's time to announce the Best Paper Awards. The Best Paper Award to the first technical session, Nanophotonics, goes to Nimmi A.V., Department of Physics, University of Kerala, India. Nimmi A.V., Department of Physics, University of Kerala, India. Second technical session, Optronic Materials. The Best Paper Award goes to Shruti Sharma, Department of Physics and Material Science and Engineering, JP Institute of Information Technology, Uttar Pradesh, India. Shruti Sharma, Department of Physics and Material Science and Engineering, JP Institute of Information Technology, Uttar Pradesh, India. Third session, Signal Processing. The Best Paper Award goes to Ashwati SS, Department of Optoelectronics, University of Kerala, India. Ashwati SS, Department of Optoelectronics, University of Kerala, India. And the fourth technical session, Laser Applications. The award goes to Swati M. Krishna, Advik Research and Development Private Limited, India. Swati M. Krishna, Advik Research and Development Private Limited, India. Fifth technical session, Photonic Materials. The award goes to Bibli Baby, School of Pure and Applied Physics, Mahatma Gandhi University, Kottayam, India. Bibli Baby, School of Pure and Applied Physics, Mahatma Gandhi University, Kottayam, India. Sixth session, Microelectronics. The Best Paper Award goes to Shyam Mohan P.C. Mohanan, Department of Center for Information Research, University of Edinburgh, United Kingdom. Shyam Mohan P.C. Mohanan, Department of Center for Information Research, University of Edinburgh, United Kingdom. And the last session, Nanoelectronics. The award goes to Rutuja K. Bhosle, School of Nanoscience and Biotechnology, Shivaji University, Kolhapur, Maharashtra, India. Rutuja K. Bhosle, School of Nanoscience and Biotechnology, Shivaji University, Kolhapur, Maharashtra, India. Congratulations to all the winners. Professor Sajeev John is a university professor at the University of Toronto. He received his bachelor's degree in physics in 1979 from the Massachusetts Institute of Technology and his PhD in physics at Harvard University in 1984. His PhD work at Harvard introduced the theory of classical wave localization, and in particular, the localization of light in 3-dimensional strongly scattering dielectrics. From 1986 to 1989, he was an assistant professor of physics at Princeton University. While at Princeton, he co-invented the concept of photonic bandgap materials providing a systematic route to his original conception of the localization of light. In the fall of 1989, he joined as a senior physics faculty at the University of Toronto. Professor John is a winner of the 2001 King Faisal International Prize in Science, which he shared with Nobel laureate C.N. Yang. He is also the first ever winner of Ontario's Platinum Medal for Science and Medicine in 2002. Dr. John is also the winner of the Institute of Electrical and Electronics Engineers Quantum Electronics Award in 2007 for the invention and development of light-trapping crystals and elucidation of their properties and applications. In 2011, he was selected as a Thomson Reuters Citation Laureate. Professor John was appointed as an officer of the Order of Canada in 2017 and has received Canada's highest scientific recognitions, including the Killam Prize in Natural Sciences in 2014 and the Hertzberg Canada Gold Medal in 2021. Professor John has also received the Kahneman Fellowship USA and the Humboldt Senior Scientist Award in Germany. In 2007, he was awarded the C.V. Raman Chair Professorship of the Indian Academy of Sciences. Professor John is also a fellow of the American Physical Society, the Optical Society of America, the Royal Society of Canada, and a member of the Max Planck Society of Germany. On behalf of all the RIOS members, I welcome you, Professor, to this webinar. And I also welcome all the invited guests and participants to the webinar. I will kindly request Professor Sajid John to begin the presentation.
Okay, thank you for that kind introduction. Good evening and namaskaram. It's really a great pleasure for me to participate in this webinar. Let me congratulate the student winners of the paper awards and also Professor Shankara Raman for organizing this very interesting series. My own father was actually a graduate of the University of Kerala, so it's really a particular pleasure for me to connect with this community. My talk today is about sunlight and improving solar light capture for clean energy production using a new type of wave interference-based light trapping. Photonic crystals are widely known for their light trapping capabilities, but this has not yet been fully exploited in photovoltaics. So the main message of my presentation today is that with suitable architectures, it is possible to absorb and convert more sunlight than a long-standing limit known as the Lambertian limit. And this important discovery has two remarkable consequences. First, it enables silicon solar cells to reach efficiencies as high as 31%, well above current world records. Perhaps more amazingly, this can be realized in thin, flexible films of silicon on the order of 10 to 15 microns. Now, many people use the words next generation solar. My meaning may differ from that of others. My talk today is not about perovskites or exotic compounds. It is not about the use of solar concentrators. And my talk is not about multi-junction solar cells. My talk is about silicon alone, and specifically thin film silicon. So just by way of introduction, let me remind you a few facts about conventional solar cells and solar energy itself. The sun provides an enormous amount of power to the Earth. According to the US Department of Energy, this amounts to 173,000 terawatts of solar power striking the Earth continuously. And this in turn is more than 10,000 times the world's total use of energy from all sources. On a somewhat more local level, this corresponds to 1.37 kilowatts per square meter in the upper atmosphere and about 1 kilowatt per square meter at sea level on a clear sunny day. So how does a conventional solar cell operate? Well, photons from the sun enter a semiconductor that excites electrons from the valence to the conduction band. This leads to the creation of an electron-hole pair, as you see here. And these electrons and holes then diffuse to contacts either at the top or the bottom to generate current and voltage to an external load. This migration is typically assisted by some sort of an electric field that's generated inside the semiconductor, usually caused by doping the crystal with donors and acceptors, so that there's an excess concentration of electrons in one region, those excess electrons can then diffuse to the other region until an electric field is generated that prevents any further diffusion. And when the electrons and holes are created by absorbing a photon, when they see this electric field, one charge carrier goes in one direction and the other goes in the opposite direction, causing charge carrier separation and preventing the likelihood that these electrons and holes would recombine and give away their energy. So the basic task of solar cells then, and the challenge, is to try and absorb as much energy as possible using the appropriate architecture, and then to ensure that these electrons and holes can reach their destination before recombination takes place. Now, solar cells have been studied for quite a long time, and for example, if you see on the left-hand corner here, silicon module efficiency has been increasing over the past couple of decades, and the lines here correspond to the change in module efficiency as a function of the year. The top curve corresponds to monocrystalline silicon. The bottom is a type of multicrystalline silicon. So at this point, you can expect silicon modules that you can buy which have an efficiency on the order of 19 or 20%. Laboratory cells, on the other hand, have reached a much higher efficiency, and I just list some of the different efficiency records that have been set in laboratories. For silicon, crystalline silicon, it's now at 26.8%. That has only increased by about 1.8% over the past 25 or so years. For multicrystalline silicon, which is less expensive, the record efficiency is 23.3. And this stagnation in the rise in efficiency has led to the study of a large variety of other thin film solar cells. Gallium arsenide is one of the most prominent. It has the highest efficiency of any single junction cell with 29.1% efficiency. Another one is this copper indium gallium selenide thin film, which has an efficiency close to 23. Cadmium telluride, which also has already found a number of commercial applications, is slightly below that. There's been a lot of interest and excitement in perovskites, which are very inexpensive to make. They have reached an efficiency of 26%, and organic or polymer solar cells with efficiencies of 17%. The latter two have received a lot of attention, but they suffer from stability issues, and the perovskites, as you may know, involve some hazardous materials. So despite all this laboratory activity, the industry is still dominated by silicon, and about 95% of the total production, and probably it's still the case, is associated with silicon, and 62% of that production is associated with multicrystalline silicon. And the market share of all these other thin film technologies is only still about 5% of the total annual production. So this is where the real important applications come from in silicon itself. Now we could ask, what defines the efficiency of a semiconductor, of a particular solar cell? And it depends very much on the band gap of the underlying semiconductor. And about 60 years ago, Shockley and Queisser developed a so-called thermodynamic efficiency picture of what the maximum possible efficiency could be of different solar cells based on the size of their band gap. So this is a plot showing where the energy that comes from the sun ends up as a function of the band gap of the semiconductor. So the blue region corresponds to photons that lie below the band gap of the semiconductor. So as the band gap increases, more and more photons are unable to be absorbed, and so they just get reflected. On the other hand, if the band gap of the semiconductor is made much smaller, then a lot can be absorbed, but the electron that is excited by absorbing a photon goes up very high in the conduction band and quickly relaxes by thermalization down to the bottom of the conduction band, and that is this pink region. So there's a trade-off between these two effects, and that is defined by this green curve. And the maximum occurs in the case of semiconductors with a band gap between 1 and 1.5 electron volts, and both silicon and gallium arsenide fall in that range. If we look more specifically at silicon with this band gap of 1.12 electron volts, then in fact 32% of the energy from the sun just is thermalized by the relaxation of carriers down to the conduction band edge. 19% of the sunlight falls below the band gap, and can't be absorbed. There's also some thermal effects associated with entropy that reduce the voltage. That's this gray region. And so Shockley and Queisser predicted that the maximum possible efficiency of a silicon solar cell at around room temperature is slightly below 33%. And that is assuming that all of the light from the sun that impinges on this solar cell, silicon solar cell, can actually be absorbed over the entire 300 to 1200 nanometer wavelength range. Now, silicon has a great deal of difficulty in absorbing that sunlight because it is an indirect band gap semiconductor. So here, what I've plotted in red is the spectrum of the sun as it's seen on the surface of the Earth. It looks like a black body spectrum at around 5,700 degrees, except for these dips associated with certain absorptions taking place in the atmosphere. And next to that, I've plotted the imaginary part of the dielectric constant of silicon, which is what enables it to absorb. As you can see, silicon absorbs very well below 400 nanometers. There isn't very much sunlight there. And because of the indirect nature of its band gap, is rather weakly absorbing for longer wavelengths. Here I've translated that imaginary part into an absorption length scale as a function of the wavelength. So at around 400 or below 400 nanometers, the absorption length is on the scale of tens of nanometers, but then it becomes much longer as you approach the indirect band edge. That absorption length scale is on the scale of tens of centimeters. And that creates a tremendous challenge in constructing an architecture that can absorb this broad spectrum of sunlight efficiently. And so this requires some sort of a light trapping mechanism in order to be able to capture this longer wavelength, especially near infrared sunlight. So the need for light trapping has long been known in solar cells, and in particular silicon solar cells. And this has a long and rich history. One of the approaches that people have considered from a long time back is something called statistical ray trapping, which pictures light not as a wave, but simply as a ray that can undergo reflection, refraction, etc. And so the idea behind this statistical ray trapping was that instead of having a flat solar cell, perhaps you could create some sort of a random or rough surface so that when light from the sun impinges on it, it would be deflected at some angle relative to the normal, then be reflected off the mirror at the back, come back to the top, and if that angle was sufficiently large, it might bounce back in again by the mechanism of total internal reflection, and thereby increase its path length so that absorption would take place. So the assumptions behind this simple model is that one has a randomly rough surface with perfect anti-reflection, but it can trap all internal light beyond a certain critical angle, and that the surface has a probability distribution for angular deflection of the light given by the cosine of the angle theta between the normal and the angle to which it's being deflected. So light at nearly 90 degrees has a very small likelihood of being deflected like that, but going straight through is the peak of this distribution. So you could ask, what is the probability that light that enters the structure by this Lambertian rough surface would end up escaping from the structure? Well, if you have a material with a refractive index of n, you know from high school that the critical angle of refraction is, the sign of that angle is given by 1 over the refractive index. So light would have to lie within this small cone in order to be able to escape. And you can calculate what that escape probability is, given the probability distribution of deflections. It's a simple integral over this region subtended by the cone multiplied by the distribution function, and that works out to a probability of simply 1 over n squared. So that's the probability of escape. You could ask, what is the average path length of light on a single bounce here? Again, that is 2 times the thickness divided by the cosine of the angle theta, and then weighted by this Lambertian probability distribution. Again, a straightforward integral. It gives 4 times the actual thickness of the cell. Then you could ask, what is the probability that light makes a certain number m bounces within the structure before it escapes? Well, for that to happen, for it to have m bounces, it would have to not escape in the first m minus 1 bounces with probability 1 minus p, and then escape on the mth bounce with probability p. So this function then gives the probability distribution for the number of bounces. And with respect to this distribution, you could calculate the average number of bounces. And this, again, is an elementary calculation. It gives 1 over p, which, according to our previous calculation, is given by n squared. So this gives a trapping length, which you could estimate as being the average length of a single bounce times the average number of bounces, which is 4n squared times the actual thickness of the solar cell. And for silicon, with a refractive index of about 3.5, this corresponds to an increase in the path length by about a factor of 50. So far, no real solar cell has even achieved this Lambertian limit. And what I'll suggest is with photonic crystal architectures, which treat light not as a ray, but as a wave, it is possible to well exceed this limit, this long-standing benchmark that has been used in the solar cell industry. So what I'll show is that with wave interference-based light trapping, using a photonic crystal, and in particular the higher bands of that photonic crystal, one has an unprecedented route to solar absorption power conversion efficiency using thin film structures which can cause this type of trapping. Some of the underlying physics is associated with an enhancement of the electromagnetic density of states inside the structure, effects such as parallel to interface refraction, slow light modes, which increase the dwell time of light, which enables 98% of the solar energy over the entire 300 to 1100 nanometer range to be absorbed with only 10 microns of silicon. And what this implies is that with solar absorption beyond the Lambertian limit, it's possible to make solar cells out of silicon much thinner and also flexible. And this reduces recombination losses because it's much thinner, such as Auger recombination. And remarkably, we predict that these thin, flexible silicon solar cells made in photonic crystal architectures could reach, in principle, efficiencies as high as 31% compared to the current world record of 26.8%, which is based on a cell which is over 100 microns thick, and the thermodynamic limit of 32.3%. And I'll show you some pictures of photonic crystals that have been fabricated either by wet etching or dry etching methods, and some early optical measurements that support this idea. So let me just talk a little bit about some of the underlying new physics that you might expect from periodic dielectric structures, such as the one that I've shown here. Consider a thin film of some sort of photonic crystal. You don't have to take these circles literally, but it's something periodic, and different wavelengths of sunlight impinging on it from the left from different angles. And you can ask how much light would be absorbed if this structure were made out of silicon. Well, this depends on a number of different factors. It depends on the quality factor of optical resonances in this structure, the nature and the density of these electromagnetic resonances, and the coupling efficiency of light, external light, into those resonances. So if you have a periodic structure like this, one thing that can happen is that light can bounce back and forth inside the structure many times before it reflects or is transmitted. This is what we refer to as slow light. Here I depict a band structure diagram of a two-dimensional periodic structure. This is wave vector along the horizontal axis and A over lambda, or frequency, in the vertical direction. You see, for instance, at this frequency, there's a band, this red dashed line, which is very flat. That means that the group velocity of light is very slow. That means that light is bouncing back and forth inside the structure as it's propagating through. And then you can ask, what is the deflection angle of light into this structure? That is the law of refraction, which is governed by the principles of energy conservation and momentum of the photon perpendicular parallel to the interface of this structure. And that is determined by the surfaces of constant frequency inside the structure. So here I plot certain surfaces of constant frequency. Since this is a square lattice, this has sort of a square-like shape. So light that is coming in at a particular direction, say by this black arrow, finds a surface of constant frequency corresponding to that same frequency, and the direction of propagation of the light is in the direction of the group velocity of light, which is perpendicular to the isofrequency surface. So the light is deflected in the direction shown by this black arrow. So it would actually be deflected in a direction that is parallel to the interface. That further extends the dwell time of light. So it's not just going straight through and out, it's being deflected nearly parallel to the interface. So with that introduction to the underlying physics, let me now talk about some actual structures that we've been considering and how we evaluate the light trapping capabilities of these different structures. So the way in which we can measure the amount of light trapping is by calculating something known as the maximum achievable photocurrent density. What this is simply taking the AM 1.5 solar spectrum, that red curve that I showed you at the beginning, which looks like a black body spectrum as a function of wavelength, multiplying that by the absorption coefficient of a particular structure. That's something that we have to calculate. It's something between 0 and 1, dividing by hc over lambda, which is the energy of a photon at wavelength lambda. That gives the number of photons at that wavelength, and then multiplying by the electronic charge, which then converts that light into an effective photocurrent density. And this absorption is something that we calculate by numerically solving Maxwell's equations inside the structure using either a finite difference time domain or FEM method. And two of the recent types of structure that we focused on recently are shown here, mainly because of the ease of fabrication. One is an inverted pyramid type structure, which can be created by wet etching on the surface of silicon, namely a potassium hydroxide etching process, preferentially exposes the 1-1-1 surface of silicon if you start with a 1-0-0 surface, and you can create these nice inverted pyramid structures. This is something that was created at the Melbourne Center for Nanofabrication using wet etching and electron beam lithography. Another structure is what we refer to as parabolic pore structures that can be created by reactive ion etching or plasma etching, again using some sort of a mask. And now we have the capability, thanks to one of your previous speakers, Professor Saulius Jodkasis, of creating anything in between these two structures by direct laser writing and some form of plasma etching. And so these are the structures that we're focusing on. The lattice constant here is spacing is about 1.2 microns. In this picture, the lattice spacing between inverted pyramids is about 2.5 5 microns. So the use of inverted pyramids actually has a pretty long history, going back to one of the early world record solar cells, which was created by Martin Green's group in Australia nearly 24 years ago. That led to the creation of this 25% efficiency solar cell. The thickness of that solar cell was about 450 microns. They were interested in ray trapping effects rather than wave interference. So the lattice spacing between the inverted pyramids in their case was about 10 microns, much larger than the wavelength of light. And more recently, we have been studying situations where that lattice constant is much smaller and comparable to the wavelength of light, to see if we can enhance the absorption of light in much thinner structures than this enormously thick 450 micron structure. So we started out by doing simulations on these structures. The parameters involved are the height, the thickness of the silicon, the lattice spacing, and the width of the mesa, which is this parameter d. And here you see some calculations using finite difference time domain of the photocurrent density that can be obtained as a function of the lattice constant A of these structures for these different structures of height ranging from 3 up to 10 microns. So at 3 microns, the optimum lattice constant is about 1.3 microns. As you make it thicker, at 5 microns, it's about 1.9. And then finally at 10 microns, the optimum is 2.5 micron lattice constant. And here we see a photocurrent density of about 40 milliamps per square centimeter. And that should be compared with the total available sunlight in the 300 to 1100 nanometer range, which is 43.5 milliamps per square centimeter. And we find that a further improvement is possible if one adds an anti-reflection coating on top of this, say silicon dioxide, and one makes the mesa, this parameter d, as small as possible, maybe as little as near 0. This increases that photocurrent density of up to 42.5 milliamps. So with this very thin structure of only 10 microns in thickness, we can absorb about 98% of the sunlight within this broad range of wavelengths, despite the very weak intrinsic absorption of silicon. Here's a more detailed picture of the absorption, showing the spectrum of absorption as a function of wavelength. And here again, you see structures of different thickness ranging from 3 to 10 microns, starting from the red curve going up to the black curve. As a function of wavelength, you see these oscillations in the absorption. These are the signatures of optical resonances taking place in the structure. And so the absorption is getting pretty high in this region where you're very close to the indirect band gap of silicon itself due to the very slow light effects. And we can even extend this into the very far region of the infrared, near infrared, from 1100 to 1200 nanometers, where the inset refers to the 10 micron thick structure, where again, due to these resonances, we're still absorbing about 40% of the sunlight in that range. And as I mentioned, if you add an anti-reflection coating on top of this inverted pyramid structure, you can typically gain an additional 2 to 3 milliamps per square centimeter. So this red curve is without anti-reflection coating, or ARC as we refer to it, and the blue curve is with the anti-reflection coating. And so here you see at 10 microns, we're up to really about 42.5 or slightly higher milliamps per square centimeter. We have some experimental confirmation of these effects, and this was experiments that were performed by my colleague Sean Lin, who created the first of these parabolic pore structures. He's at Rensselaer Polytechnic Institute in New York. So here you see the structure that he made, a depiction of it. There's silicon in blue. Underneath that, there's a small buffer region of silicon dioxide, maybe about 100 nanometers in thickness. And this is the silicon dioxide anti-reflection coating that's placed on top of the silicon. The red curve shows the Lambertian limit as a function of wavelength from 300 to 1200 nanometers. And the blue curve is the actual experimentally observed absorption coefficient. So you do in fact see these absorption resonances at these long wavelengths. And below that is the green curve, which corresponds to the calculated absorption spectrum, which likewise shows these absorption resonances. This is the AM 1.5 solar spectrum superimposed below it. The theory was done at normal incidence. The experiment was actually done at slightly off normal incidence. So there's some slight differences between the theory and the experiment. But here's a table summarizing the results of what is observed experimentally in the different wavelength regions, 300 to 1100, as well as 1100 to 1200, and the total. So the experimentally observed photocurrent density turned out to be 41.52, which is well above the Lambertian limit, which for this structure would be 39.63 milliamps per square centimeter. The theoretical estimates shown in the first two columns are slightly below that. That's probably because we didn't have an exact rendition of what the actual structure is, and we were dealing at a slightly different angle of incidence than the experimental structures. But this does show very clear evidence that one can exceed the so-called long-standing Lambertian limit. We've also done detailed experimental studies at other angles of incidence in both the inverted pyramid structure as well as the parabolic pore structure shown on the right, at angles of incidence ranging from 10 degrees up to actually up to about 60 degrees. And this shows the change in the absorption spectrum as you go more and more off normal. The absorption remains pretty good in the inverted pyramid structures until you reach about 40 degrees off normal, where it starts to get smaller. We're down to about 38 milliamps here. In the parabolic pore structures, we start at 10 degrees off normal, 42 milliamps, and it only decreases to about 41.6 at 40 degrees off normal. And this is a chart or table showing the different photocurrent densities all the way up to 60 degrees off normal. And again, you see the TP structure, which we call parabolic pores, still maintaining about 41 milliamps per square centimeter up to 60 degrees. And this is over a slightly different wavelength range. This is from 330 to 1200 nanometers wavelengths, where the Lambertian limit is actually 39.5 milliamps per square centimeter. And as I mentioned, the new fabrication capabilities by Professor Jodkes actually allow you to create structures that interpolate between these two structures for a wider variety of possible light trapping structures. So we can look in more detail as what is happening inside of each of these optical resonances. And this is a depiction of what happens at two particular resonances at 1008 nanometers and another one at 1040 nanometers. What is depicted here is the light intensity inside the structure. So this is the outline of the inverted pyramid here. This is the bottom rear reflector of the solar cell. This is for a 3 micron thick structure and below a 10 micron thick structure. You see high intensity spots where the light is being focused. That's the red regions. And the blue regions are where the light intensity is smaller. The yellow arrows represent the pointing vector of the electromagnetic field, showing the flow of energy in the resonance. And what you see, it's maybe a little bit hard to see in this depiction, but you see a lot of circulation of the pointing vector. So the light is undergoing vortex-like circulation, as well as a large amount of this parallel to interface flow, which is increasing its dwell time and allowing this long wavelength light to actually be absorbed. What is important for solar energy and the efficiency of the solar cell is integrating over all the wavelengths associated with these different resonances. and creating what's called an optical generation profile. That's shown on the right. So this is the total density of electron-hole pair that is being created per unit time within a 10 micron thick solar cell with an inverted pyramid at the top, showing just one unit cell. This is in a logarithmic scale, so 21 refers to 10 raised to the power 21 per cubic centimeter photogenerated carriers. So quite a lot of the photogeneration occurs near the top of the cell, and then still a fair amount towards the bottom of the cell, where this number goes down to 10 raised to the power of 20. And to determine the efficiency of the cell, we have to determine how efficiently these photogenerated carriers can reach contacts that have been placed in the cell. So again, this is the Shockley-Queisser picture showing that what is the maximum thermodynamic efficiency at room temperature, slightly below 33, or it's actually 32.3% for silicon. And we certainly can't absorb all of the sunlight, but with light trapping, we can absorb a fair amount of the available sunlight. And now we have to describe how electrons and holes move or migrate once they are generated. And that is described by means of what are called the semiconductor drift diffusion equations, which are listed here. The first equation is just an electrostatic equation, or Poisson's equation. Psi is the electrostatic potential, epsilon is the dielectric constant, Q is the electronic charge, P and N are the densities of holes and electrons in the structures, and Nd and Na are the donor concentrations. The second two equations are just continuity equations, the divergence of the photocurrent of both electrons and holes, which is influenced by this generation rate, G, which is this integral over all wavelengths of the absorption. And then there's also a very important recombination rate, which I'll talk about, due to recombination of charge carriers. And the last two equations are constitutive equations, saying that the current is being generated by the electric field generated by the gradient of the static electrostatic potential, and the gradient of the carrier concentration, which is this gradient of N, or the gradient of P. And there's a diffusion coefficient for the charge carriers and a mobility of the charge carriers given by D and mu. So then we have to solve this coupled nonlinear set of equations together with the Maxwell equations for the generation rate to actually find the efficiency of the cell. So it's a very complicated exercise, but first let me talk about some of the recombination mechanisms that define what the real limiting efficiency is. So in the bulk of silicon, there are three possible recombination mechanisms that one needs to consider. One is that the electron that has been excited to the conduction band edge recombines with the hole at the valence band to re-emit light. That is very unlikely to happen because silicon is a indirect bandgap semiconductor. A second important effect is due to defects inside the structure, say dangling bonds or dopants, which create defect states inside the gap. So the electron and the hole can get trapped at these defects and then recombine non-radiatively, giving off thermal energy, and that energy is lost. And the third is an intrinsic effect due to the Coulomb force between electrons, so that an electron that's excited here can fall down to the valence band, but instead of emitting light, the energy can go into exciting another electron in the conduction band to a higher energy, and that then relaxes back by thermalization back to the top of the conduction band, and this is referred to as Auger recombination. So no matter how high a quality of silicon you create, you cannot get rid of this Auger recombination, so this is considered intrinsic. So about 10 years ago, a group in Germany, co-authors here, Richter et al., defined what they thought would be an efficiency limit to silicon solar cells based on the assumption that the maximum amount of light you could absorb is given by the Lambertian limit, and that one has only this intrinsic Auger recombination loss. So here's a plot of efficiency that they made versus the thickness of the solar cell. So as you make the solar cell thicker, you can certainly absorb more light. That's good. But as you make the solar cell thicker, you also create more recombination effects, especially Auger recombination. So there's a trade-off between these two effects. And if you focus on the red curve at the top, it suggests, that this is their calculation, that the actual optimum thickness of a silicon solar cell would be at about 110 microns in thickness, and that the maximum possible efficiency, the limiting efficiency, would be around 29%, assuming Lambertian light trapping. What we have shown or suggested in contrast to that is if you involve wave interference-based light trapping structures, that the optimum efficiency is actually not 110, but it's down to a 15 micron structure, which has much less Auger recombination, and the real efficiency limit for a silicon solar cell is rather closer to 31% rather than their prediction of 29%. And that 29% already ignores all of these trap-assisted recombination, sometimes called Shockley-Reed-Hall recombination, as well as surface recombination. So the other extremely important feature of silicon solar cells, or any solar cell, is recombination of processes that can occur at the surface of the structure. The surface of a structure can have defects, for example, dangling bonds, which are not bonded to any other silicon. Those create defects within the band gap and trapping centers for electrons and holes, where very rapid recombination can take place and most of the energy can be lost. And a lot of effort in photovoltaics has been focused on trying to create surface passivation techniques for reducing this surface recombination. So one that has been used by a colleague of mine at the University of Toronto, Professor Nazir Karani, is to deposit a thin layer of both amorphous, hydrogenated silicon that is heavily doped and also a small layer that is undoped. What that does is that the hydrogen can cap these dangling bonds, and the heavily doped amorphous hydrogenated silicon creates donors that can create an electric field at the surface, which prevents one of the carriers from reaching the surface. And for recombination to take place, both carriers would have to be present. And with this surface passivation technique, they have shown that the recombination can be reduced quite a bit. That is measured by something called the surface recombination velocity. The meaning of surface recombination velocity is the recombination rate per unit area per unit carrier density. That actually has the units of velocity. And they've shown that the velocity, this recombination velocity, can be down to about 10 centimeters per second. And just for comparison purposes, if they did nothing to the surface and left the surface unpassivated, that recombination velocity would be on the order of 10 raised to the power of 6 centimeters per second. So this is a great reduction in the recombination rate. Another approach that we're following with the help of a group in Germany, which actually set one of the recent world records for silicon solar cell efficiency of over 26%, is to deposit a layer of aluminum oxide on the top of silicon. That also creates a strong electric field that can deflect what are known as minority carriers from the surface, and also leads to very effective surface passivation, leading to velocities on the order of 2 to 10 centimeters per second. And on top of that is a silicon nitride layer and a silicon dioxide layer that provide anti-reflection coating. And they use something that's called interdigitated back contact configuration, which moves both the positive and negative contacts to the bottom of the cell, shown in the two sets of black regions at the top of the cell, so that there's no shadowing loss or reflection of light at the surface due to the presence of contact. So this is another way of allowing more sunlight to be absorbed. So this is the design of the structure that we're actually considering. It's slightly different from the one by the German group, but quite similar. It consists of an inverted pyramid structure on the top with a spacing of pyramids on the order of 3.1 microns. We consider a dual layer anti-reflection coating on top and a heavily doped P region on top, which also provides a front surface field to deflect minority carriers. And then we consider this interdigitated back contact geometry with doping regions above these contacts, again, to prevent minority carriers. Here's a side view of the same thing, showing the silicon dioxide is shown in red here. Orange and blue show the heavy doping regions. The green region is lightly doped silicon with a doping of about 5 times 10 to the 15 cubic per cubic centimeter. So we have to solve the generation rate inside the structure using Maxwell's equations and then solve the drift diffusion equations inside the structure to calculate the efficiency. And that's something you can find more details of in this reference. Before I do that, let me ask what would happen in the case of a Lambertian cell, where we assume that light trapping is by ray optics only. So this shows what the efficiency of such a cell would be, a Lambertian cell would be, as a function of its thickness. And here we actually assume a realistic state-of-the-art surface recombination velocity of 10 centimeters per second. We also introduce some losses due to bulk defects, which is described in terms of a Shockley-Reed-Hall lifetime, which we take to be 10 milliseconds, which is essentially the state-of-the-art for the best quality silicon available. And what this shows is that with Lambertian light trapping, with some of these realistic but very high quality silicon, that the optimum solar cell would occur at a thickness of 90 microns, and the actual efficiency would be slightly over 28%. This is also the open circuit voltage as a function of thickness, which decreases from about 0.78 or so and goes down to 0.73 at very thick solar cell. This is the photocurrent density, which increases with the thickness of the solar cell, but the efficiency involves the product of this velocity and the short circuit current, so there's an optimum value of that. So now we move to the light trapping based on wave interference and inverted pyramid structures, and we do some optimization for different thicknesses of silicon, ranging from 3 microns up to 15 microns thickness, and look at what the maximum achievable photocurrent density would be as a function of the lattice constant, or spacing between the inverted pyramids. So here, I'll just focus on the top curve here, which is a 15 micron thick silicon structure, which we find has an optimum lattice constant of about 3.1 microns. And a larger lattice constant is easier for fabrication purposes. So that's what we focused on. If you go to thinner structures, the optimum lattice constant for 10 microns is 2.5 and gets smaller and smaller. So this is the MAPD in the 300 to 1100 nanometer range using a dual layer anti-reflection coating, slightly different from the 3-layer anti-reflection coating used by the experimental group. Here's a summary of the photocurrent densities, optimum lattice constants, and the Lambertian limit for this range of silicon thicknesses ranging from 3 to 20 microns. So again, for 15 microns, the optimum lattice constant is 3.1 microns, and the Lambertian limit would predict that the maximum photocurrent density in this case is slightly over 40 milliamps. In our case, based on solution of the Maxwell's equations and wave interference light trapping, we find that in the 300 to 1100 nanometer range already 43 milliamps, and an extra 1.3 milliamps in the 1100 to 1200 range, leading to slightly over 44 milliamps per square centimeter. So with this light trapping mechanism, we are exceeding the Lambertian limit by between 3 and 4 milliamps, which is a very substantial increase in the solar absorption and in a very thin structure. So here you see the actual calculated efficiencies that we have obtained by solving both the drift diffusion equations and the Maxwell's equations. efficiency as a function of cell thickness. And again, we use some realistic but state-of-the-art numbers for the quality of silicon as described by the Shockley-Reed-Hall lifetime, which we take ranging between 10 milliseconds, which would be the highest quality silicon, down to 0.1 milliseconds, which would actually correspond to a type of good quality polycrystalline silicon. And we show that in this, first of all, in the case of the highest quality silicon with 10 millisecond lifetime, that's the blue curve on top, that the efficiency increases with the thickness, but then reaches its maximum at 15 microns thickness and then starts to go down again. And that's close to 31% efficiency. And if you now make the quality of the silicon lower, the optimum thickness becomes smaller. As you come down to the worst quality silicon, this black curve here, with a lifetime of only 0.1 milliseconds, the optimum thickness is now down to 7 microns. But even then, the predicted efficiency is slightly over 27%, which suggests that a 7 micron thick structure consisting of polycrystalline silicon could achieve this unprecedented world record type of efficiency. And so here again, we've assumed a surface recombination velocity of 10 centimeters per second. If you were to increase that surface recombination from that value, these efficiencies would get much worse than the predictions that have been made here. And here are some actual numbers for the exact contact geometries for the P and N contacts, the size of the contacts at the bottom, and the actual doping concentrations that we would use. And if you're interested in the numbers, you can look at the actual paper that we've published. Okay, so finally, let me show you a summary of the different structures that we've considered together with a comparison with 3 of the world record solar cells that have already been demonstrated. So this is a curve at the top showing the photocurrent density of various solar cells as a function of the thickness of the solar cell. The curve, the points at the bottom, the diamond here is the 26.1% cell created by the group in Germany a few years ago. The cross here is the 26.7% cell created by the German group, by the Japanese group, and the star here is the 26.8% cell generated by Longyi in China. The blue curve is the Lambertian limit, so you can see that all these solar cells fall below the Lambertian limit for photocurrent density. The wave interference-based light trapping structures that we've shown are shown above here, starting from 10 and 15 microns, 50 microns, 100 microns, and then 150 microns and thicker. You can see that even at 15 microns, we are getting a predicted photocurrent density that's well above the Lambertian limit and already comparable to these world record cells. And if you apply this wave interference to even these thicker cells, there's a great deal of room for improving the photocurrent that could be generated in these cells by a more efficient light trapping mechanism. And this is a list of some of the people that have been involved in the collaboration that we're now engaged in of trying to combine the surface passivation effects at both the bottom, the contact geometry, and at the top, with the microstructuring on the top surface using some inverted pyramids. A couple of the PhD students that have been involved are Michael Rienecker in Germany and Jovan Maximovich in Saulius's, Professor Jodkas's group. And this is the leader of the German group, Professor Robbie Pipe. So we're hoping for some interesting outcomes by trying to combine both the electronics and the optics, and hoping that we can manage to still passivate the surfaces very well, even though we're applying this novel type of microstructuring on the top surface. Okay, so let me summarize then. I hope what I've convinced you is that photonic crystal light trapping can enable near perfect solar absorption in thin films, even though we're dealing with an indirect bandgap semiconductor such as silicon, which would in turn allow a major reduction in bulk recombination losses. Some of the underlying physics is the wave interference, which leads to parallel to interface refraction effects, high electromagnetic densities of states, slow group velocity modes, and other optical resonances. The best case that we've considered is a power conversion efficiency obtained by solving the combined Maxwell equations and semiconductor drift diffusion equations, with modeling suggesting up to 31% efficiency with 15 microns of thickness if everything is done ideally. And this is at 1 sun power and a surface recombination velocity of up to 100 centimeters per second. If you use solar concentrators, that can actually increase the efficiency further. With 60 suns, this goes up to 34%. And I should emphasize that it very much depends on the surface passivation. There's a very rapid loss of efficiency, as there would be for any solar cell with improper front and back surface doping and passivation. In fact, you can reduce this down to 5% efficiency if those surfaces are not passivated at all. And finally, another very nice feature of photonic crystal solar cells is that they exhibit very good angular response from normal incidence up to about 50 degrees off normal without losing much of the efficiency. So with that, I think I'll stop and take any questions if there are. Thank you.
Good evening all. So we have reached the end of the last and valedictory webinar session of ROSE 2023. I deem it a great honor and privilege to propose a vote of thanks for this great event, ROSE 2023, organized by the Raman International Optronics Society, RIOS, in association with the Department of Optoelectronics, University of Kerala, India, and LELS, University of Nova Gorica, Slovenia. On behalf of the RIOS and the entire organizing team of ROSE 2023, I extend a very hearty vote of thanks to our distinguished professor, Professor Sajeev John, University of Toronto, Canada, for gracing your important work and sharing with us your findings and opinions towards the talk on photonic crystal light trapping for next generation solar energy harvesting. I must mention our deep sense of appreciation for you, sir, for giving excellent coverage to topics such as conventional solar cells and its optical performance, opportunities for solar energy harvesting, solar light trapping, advances in surface passivation of silicon solar cells. Once again, we thank you, sir, for your outstanding presentation. Now, a special thanks to chairpersons, vice chairpersons, secretaries, and advisory committee members for their encouragement, support, and coordination to make this webinar successful. We are thankful to all the eminent personalities, professors, faculties, and students across the world who joined the webinar and participated actively. We greatly acknowledge the contributions of the organizing committee and members of RIOS for the successful completion of the webinar series ROSE 2023. A hearty congratulations to the winners of Best Paper Awards. The abstract book with ISBN number of ROSE 2023 can be downloaded from the website, and the results of Best Paper Awards can be viewed in the notifications page of the RIOS website. I humbly request all of you to join for the ROSE 2024 and to propose eminent speakers of your choice. Thank you all for making today's event successful with your contribution. All the participants are requested to submit their feedback form today itself within 2 hours. The link to the feedback form is available in the chat box. Once again, we thank you all for being with us, and we hope to look forward to your involvement in the upcoming webinars to make this series a tremendous success. Have a good day. Thank you.